Alrighty, happy Tuesday. Hope everyone's doing okay. Ideally, counting down the days, maybe weeks, until school is done, and hopefully summer has more fun things than watching Zoom calls about algebra and Spanish and history and SAT and ACT. So then what I'm going to do is start running through kind of everything we think we need to know about algebra for the test. Okay, so I'm going to start from like really simple algebra stuff and go it up through kind of the nasty stuff that I've seen on tests. I suspect that you've all taken algebra. Ideally, doing algebra 2, maybe onto pre-calc, but even though we've done that stuff, we might be a little bit rusty. So really simple stuff. X squared times x cubed is, of course, x to the 5th. X squared plus x squared is not x to the 4th, but of course is 2x squared, just like a k plus a k would be 2k. X squared plus, you can't do a lot with that, sadly. What you'd have to do for that, you could factor out an x squared and do that, but generally there's not a lot we do with those guys together. More typical things, people might get something like 2x plus 6 over 2x. Sometimes people have a tendency to want to simplify those. You can't do that, sadly. If it were 2x plus 6 minus 2x, those guys can cancel out, but we can't do this because what we really have is 2x over 2x plus 6 over 2x, so I can't just cross out one part. What I could do if I wanted to is factor that and take a 2 out of both the 2x and a 2 out of the 6. So I have 2 times x plus 3 over 2x, and then I could cancel the 2 out of both and have x plus 3 over x. So that's permissible, but that other business not so much. Slightly more complicated thing, you might get something like x plus y over x minus y equals 2/3, and then the question might ask, what does x over y equal? That sometimes flummoxes people a little bit. From my perspective, a lot of things that are set up as ratios or set up proportions are kind of most easily handled by cross-multiplying to undo them. So I'd have x plus y times 3 equals 2 times x minus y. So 3x plus 3y equals 2x minus 2y. Then, as you know, we're putting the x's together. Minus 3y, minus 3y. So that x equals minus 5y. If I want x divided by y, divide both sides by y, and I'd have x over y equals minus 5. If you had 3x plus 2y over x minus y equals 1 over 2, same thing, cross multiply. Put like terms together and isolate. So kind of basic stuff with algebra. You can certainly get problems that ask you, and this we'll start with this and we'll end with a really mean version of this at the end. So I might have to do something like that, and they ask you, if you have ax squared plus bx plus c, ask what a plus b equals. So what do? We FOIL that, and people may know that term, which stands for first, outer, inner, last, right? So first term's x times 2x, again, is not 2x or 3x, it's 2x squared. And then the last term's minus 3x. Inner, 2 times x, and again, if this is old hat for you or long ago or review, I apologize if I'm boring you, but I want to get everyone kind of on the basics, and then we'll go through harder and harder stuff. So first terms, outer terms, inner terms are here, and then the last terms, and then as always, we put like terms, like terms together, minus 3x plus x, and that would be our answer. The flip side to that could be factoring. And they might ask, what are the values of x? So for that, we are trying to say, these terms have to multiply to equal that. The last terms have to multiply to equal that. And then these terms have to add to equal here. So I'm trying to find what two numbers multiply to equal -10 and add to be -5. So something like -5 plus 2. I know there are different methods that people have for this. Put it in the box. I tend to just kind of run the numbers in my head and say what times what equals that and adds to that. Multiply to -10 and add to -3. So if I had that, if they're asking me what is x equal, if x minus 5 equals 0, this means depending on the language on the SAT versus ACT, finding the solutions, finding the roots, lots of different ways to describe that. So I'd say x minus 5 equals 0 and x plus 2 equals 0, which means that my root or my solutions to this would be x equals 5 and x equals -2. You get something going the other way if the roots or the zeros or solutions of, let's say, ax squared plus bx plus c equals 0 are 3 and -5. Find, oh, I never finished that one up at the top. 3 and -5, find what b equals. So if my roots are 3 and -5, that means x equals 3, that means my factor is x minus 3 equals 0. I have minus 3 from both sides. X minus 3 equals 0. Here I add 5 to both sides. X plus 5 equals 0. So then if my factors are x minus 3, x plus 5, I can then FOIL that out the same way I did the other one. Instead of x squared, sorry, I ran out of room, x squared plus 2x minus 15 equals 0. So the coefficient before the x squared a would be 1, before the b would be 2, and for the c would be -15. Okay? So basic factoring, basic FOILing. If you had 2x squared minus, I don't know, 10x minus 14 equals 0, I can factor 2 out of everything and then try to factor that. Now, what happens, you may have already figured out, that's not going to factor very happily. So how do I find the roots of this if it doesn't factor? Well, hopefully a bunch of you remember what's called the quadratic formula, which says for a quadratic in standard form, the roots or the zeros are the solutions to it. We use the term zero because it's the idea if you had a function, you set the whole thing equal to 0 and find the values of x that make that equal to 0, right? These are also known as the x-intercepts for that, okay? All right, so not a happy thing to factor. I can't think of numbers that work well, so I'll use the quadratic formula. Quadratic formulas people may remember is that x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Now I'm going to do this problem here that's relatively straightforward. Then I'm going to get into some gnarlier stuff. Some of this you guys may have learned and you've forgotten. Some of this you may have never learned and think I'm crazy. Then this part will be relatively typical kind of out of an 800 math level, probably a 500, 600 level problem. The ones I'm going to do thereafter are pretty sophisticated. So if you're a little whoa about it, don't panic. It's definitely some more sophisticated stuff. But taking this problem, x squared minus 5x minus 7 equals 0. If I want to assign the solutions, just to help you out, this is a is 1, b is minus 5, c is minus 7. So -b minus 5 plus or minus the square root of b squared -5 squared minus 4. A was 1. C was -7. Lots of numbers I know, all over 2a, which is 2 times 1. -5 is plus 5. I'll just talk my way through this. -5 squared is plus 25. Now keep in mind, sometimes people on a calculator type -5 and then squared, and the calculator tells them it's -5. But you know that a negative squared is positive. So if you do that on a calculator, that's okay. Just make sure you use parentheses or check that a negative times a negative is in fact positive. So back to here, -5 squared, 25, minus 4 minus 7, plus, minus becomes plus, 28. Oh, this is going to be an unhappy number. So 5 plus or minus the square root of 53. Good grief, what an ugly number. Now, You might be thinking, can I just put this on my calculator? Well, if you have a program or an app on your calculator that has a quadratic formula, absolutely you may use that. The SAT and the ACT allow you to have these things if they come along with your calculator. You may use these. But as you might expect, on the SAT, this would be a problem that would be much more likely to be on section 3, the non-calc section, in which case, well, no luck, you don't get to use a calculator. And so we just have to do all this work by hand, and the answer choices wouldn't be expressed in some wacky decimal. They'd be expressed this way. And you just walk through the answer choices until you find this one. On the ACT, you could, of course, use this, but if you put this on your calculator, if you can find this, but if you did it with just pure arithmetic and got a funky number, you'd have to go through the answer choices anyway. So sometimes a calculator is easier, sometimes actually walking through the math is easier. But let's go back to the quadratic formula, and again, I'm going to show you the hard version of this. So again, ax squared plus bx plus c equals 0. We said x would be negative b plus or minus, just to and then I'm going to show what the curveball version of this is going to be. Now, you may know this, but what I want to talk about is what happens with b squared minus 4ac. What happens if that's equal to 0? What happens if that's greater than 0? What happens if it's less than 0? Okay? And you may have done this, but again, if we talk about the roots, or the zeros, or the solutions to this, if b squared minus 4ac equals 0, we would end up with one real root, meaning real meaning non-imaginary, not the square root of a negative number. Why is that? Well, if you go back up here, if this whole thing inside here is equal to 0, you would have negative b plus the square root of 0 all over 2a, so negative b over 2a, or negative b minus the square root of 0. Well, plus the square root of 0 minus the square root of 0 is the same thing. Negative b plus square root of 0, negative b minus the square root of 0. Because the square root of 0 is just 0, we just get negative b over 2a. So we get one real root. Some of you may remember that when we have one real root, we're tangent to the x-axis. We hit it in one place. So this could be something like, I don't know, x squared minus 9, minus 6, excuse me, plus 9 equals 0. If you factor that, x minus 3, x minus 3. So you get x equals 3 would be your only root. You'd have a double root of 3, 0. Now, curiously, I'm going to come back for a moment. Some people know that that's the vertex. I'm going to come back and talk about that in a second, okay? I'm going to come back up here. If b squared minus 4ac is greater than 0, then this number up here isn't 0. It's negative b plus square root of 2 minus the square root of 2 plus 1.2 minus 1.2, whatever. That will get me two real roots. And that will look like, if I go down here, that will look like something like that. I will get two real roots, okay? The negative b over 2a is still the point right there, and then it's plus this amount minus this amount. That will give me two different roots. If it's less than 0, I would then have the square root of a negative number, and that would get me two imaginary or two complex roots. Imaginary number, of course, is the square root of negative 1. We'll talk about that in a moment. So if you had 3 plus or minus the square root of negative 4, that would be 3 plus 2i, 3 minus 2i. 3 plus or minus the square root of 4 is 2, and the square root of negative 1 is I. So that gets us two complex roots. So again, this is pretty sophisticated stuff if you guys are aiming for higher level questions. We'll do this one more time and higher scores. Equal to 0, one root. Greater than 0, two real roots. Less than 0, three real roots. That's funny. Two imaginary roots. I'm getting carried away. So one real root, tangent to the x-axis. Two real roots does that. Two complex or imaginary roots sit up there. We talked about when it was tangent here that this point, when it was tangent, was one real root. That point was negative b over 2a. That, as you may remember, is the formula for how we get the vertex of a quadratic. This point would be negative b over 2a. But then if I wanted to find the y value, I would stick that back into my quadratic and find whatever the y value is. Here, that vertex will be imaginary and more complicated. But if you have 3 plus 2i, 1, 2, 3, but this is more ACT than SAT, the 3 would be on the real value would be on the x-axis and the imaginary on the y. So we'd be there. A little more complicated than most people, what we'll see on very many problems. Okay, so we've talked about foiling, we've talked about factoring, we've talked about the quadratic equation. We talked about the vertex, which is negative b over 2a. And may do, if we have time, we'll talk about completing the square, which is pretty complicated stuff. We may come back to that. And then imaginary numbers, we said, were the square root of a negative number. So you have negative 4. That's the square root of 4 times the square root of negative 1. Square root of 4, we can do plus or minus 2, and then we have I, plus 2 minus I. So really quickly, just to run through this, I squared, I cubed out of the 4th. If you have a T83 or 84 handy, you can throw these right on your calculator, and that will give you the square root of negative 1. It's on your calculator. It's the second decimal button. So if I did this, I'll show you some of these, and then show what we have to do without a calculator. So if I did I squared, I squared, I would get negative 1. If I did I cubed, again, second decimal down there, up button 3, whoops, that's a 6, I'll get negative I. So I squared is negative 1, I cubed is negative I, and I to the 4th will be 1. Trust me on that, I won't put that on the calculator. Here's why, and I want to talk about this. Can be important conceptually. I is the square root of negative 1. I squared, I times I, the square root of negative 1 times the square root of negative 1 will always equal itself, just like the square root of 7 times the square root of 7 will equal 7, okay? I cubed would be I squared times I to the 1. I squared, you know, is negative 1, so that would be negative 1 times I, which is just negative I. And then I to the 4th, this is important, I to the 4th is I squared times I squared. Negative 1 times negative 1, as you know, becomes positive 1. Here's the really important thing. It's a repeating pattern. If you go back up to the top, I to the 5th would be I to the 4th times I, and I to the 4th we said is 1. So I to the 5th is the exact same thing as I to the 1st. I to the 6th is I to the 4th times I squared, but since I to the 4th is just 1, I to the 6th equals I squared equals negative 1, and the pattern goes around and around and around and around. So if I wanted to know, gosh, what is I to the 19th equal? What I'm going to do is take out 4s, and I'll show you how to do this with a calculator in a second. I'm taking out i's to the 4th, I guess i's to the 4th, times I cubed. 4, 8, 12, 16, and then 3 more gives me 19. This, I to the 4th, we said is 1, and that's 1, and that's 1, and that's 1. And so I to the 19th is the same thing as I cubed, which again is just negative I. If you have a huge number, if you have I to the 1014, you're like, I don't want to do that this way, that'll take me all day. Here's what we do. We'll divide 1014, whoops, 1014 by 4. 278.5. Well, what do I do with that? That means that I had 278 i's to the 4th, because 4 times 278, we'll do this on a calculator, 4 times 278. Note I take the part before the decimal, because that's how many times I went in evenly. And then I had stuff left over, what we call the remainder. So take the part before the decimal, 278 times 4, and that will give me 1,112, as I knew. So what does that mean? Well, if we started with 1,114, and it goes in this many times evenly, that means we have a remainder of 2, so that I to the 1,114 is the same thing as I squared, and I squared, as we said before, is negative 1. Okay? 2 really quick things on imaginary numbers, and I know I cover a lot of stuff really fast, but I want to make good use of your time. Oh, by the way, people asked about last week about where do you find recordings. On the email that you got from today, the email, I'll show this to you really quickly. And the email that you got from today, if I can find this, maybe it'll cooperate. Let's try that again. On the email that you got from today, you can click on PMTV. Maybe this will cooperate. You've got to be kidding me. Well, I'll try that again. We'll get there in a second. You can click on that link and then go to the page for, click on that, go to the page, there's a class page for ACT, SAT, and then on that, there's a link to every single past class. So you can find, last week we did test prep, or we did test anxiety, we did SAT, ACT at the very start, we did all the tricks of plugging the numbers. So in that email, if you just click on PMTV, it'll take you right to the pages, class pages, and then there's one for SAT and ACT, and then if you scroll down, you'll find all the recordings from the things before. I'll try to share that on my phone if it'll need to cooperate. Okay, last two things I said to imagine numbers are this. You might be asked to do what's called rationalize. If you had 2 plus 3i and 2 minus 3i. Rationalizing, you may remember, something like you had 6 over the square root of 2. Real mathematicians, I'm not one of them, so I don't care, but real mathematicians really don't groove on square roots in the denominator. So to get rid of that square root of 2, we can multiply the top and the bottom by the square root of 2. It's just like changing a fraction, right? You can multiply the top and bottom by 2, changes the look but not the value of it. So 6 root 2 becomes 6 times root 2. Root 2 times root 2, as we know, is 2. Then you can simplify it, and that will equal 3 root 2. So 6 over root 2 is the same thing as 3 root 2. This is now rationalized, meaning there's no square root in the denominator. Now, if mathematicians really get upset about 6 over root 2, you can imagine how unhappy they are about having the square root of a negative number in the denominator. That's even uglier. So the question is, how do you get rid of that I in the denominator? And a lot of people say, oh, I remember that I squared thing was -1. So if I multiply this times times I, that'd be great. The problem is, it fixes this part here. We get minus 3i squared, and that's -1, but it introduces an I over there. So we kind of fixed one part, but goofed up another. So what we're going to do for this is multiply times what's called the complex conjugate. It doesn't matter. You don't need to be, won't be quizzed on this, but it's called the complex conjugate. And the idea is this. Do you remember how x squared minus 9 factors? That is x plus 3, x minus 3. And we do that because x first, outer, inner, last, and those guys cancel themselves out, so you just get x squared minus 9. It's called the difference of two squares. 2 squared, 3 squared, then the difference, I subtract them. So this minus that. So we're going to use the same principle here to rationalize this. We're going to multiply times 2 plus 3i. 2 plus 3i. Again, lots of work on the top. Really quickly. First, outer, inner, last. On the bottom, 2 times 2, 4. Outer, inner, which cancel out, last. Here's the beautiful part. I squared, like we did on the previous page, is -1. So 6 plus 6 times -1 is just -6. So those guys zap each other. 9i and 4i, 13i. I'm going to squeeze them in right here if we can do that. 6 and -6 cancel themselves out. 9i and 4i is 13i. These canceled out, 6i minus 6i, and then 4 minus 9i squared. I squared again is -1, so -9 times -1 becomes plus 9. 4 plus 9 is 13, and oh my gosh, look at that, 13i over 13, and the whole thing just simplifies to I. Doesn't always work out that nicely, but that's what they often design it with. When you have, again, a fraction with an I in the denominator, we clean it up by we rationalize it by multiplying what's called the complex conjugate. And then the last little twist thing that you might see, this is more of an ACT than an SAT thing, but it's this. If one solution to a quadratic is 7 plus 5i, what's the other root, or the other solution, I guess, to be consistent here? And a lot of people are like, how the heck should I know that? Well, if we remember that the quadratic equation, negative b plus or minus the square root of blah, 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 negative, I'll write it out, b squared minus 4ac, all over 2a. It's negative b plus whatever this mess is going to be, all over 2a, and negative b minus all this stuff, all over 2a. So let's look at this. If one root is going to be 7, I guess that must have been minus 7 to get me that, but it's 7 plus 5i. So this number plus 5i, and I guess there must have been 1 in the denominator. Then over here we'd have 7 minus 5i. That's how quadratics with imaginary numbers have to come together. If we had a root that was 7 plus or minus the square root of 9, it'd be 7 plus 3 and 7 minus 3. So if one is this, the other one has to be that. If one is a plus bi, the other one must be a minus bi. If one is a plus 2i and the other one is 7 plus ki, that means that a has to be 7 and this has to be minus 2. Because they always follow that form, 7 plus 2i, 7 minus 2i. Again, a little in the weeds, really sophisticated. These are curveball problems that people are like, what are they talking about? They don't show up a ton. They usually show up like once every other test, but just some of these ones that are really quirky and tricky, don't worry about them, but really look more as an opportunity to kind of know what that extra credit problem might be coming along the line. You just kind of file this back in the back of your head. Hopefully you guys have been doing some work with practice and tests from Khan Academy, or have gotten that official ACT guide. We have put the practice ACT up last week. I think this week we're going to throw that ACT up again, and one of the either PSATs or SATs that we've done to give you guys some more practice there. Again, lots of stuff on Khan Academy, but in case you haven't made your way over there, we'll put them right on our website. All right, what have we done so far? We talked about kind of properties of algebra. We did factoring and foiling, talked about the quadratic equation, looked at the roots, talked about how that's the vertex for the x part imaginary numbers. Okay, we're going to back up and start with the stuff that's a little bit easier with lines and then get a little bit harder with lines, okay? This is really important because particularly for the SAT, when the SAT remade itself in 2016, they really tried to make a lot of the math be based on what people in college said are tools that people need to use in lots of different courses in college. And so you're not likely to do a lot of calculus unless you're a mathematician, maybe physicist, maybe economist in college. But you are likely to use a lot of algebra and linear, what are called linear models, linear of course just from the word line, in all kinds of things, those classes I mentioned, but also in biology or psychology or geology. These are some basic tools we need to use to represent data. And so it's pretty important stuff. So let's just start with the basics of a line. So y equals mx plus b. I know people know that, but let's just go through this. This means we can have a million different x and y points that go in there. M is, of course, the slope. Quick reminder, rise over run. We'll do some problems to reinforce that. B is the y-intercept. I wrote that poorly, I apologize. When we think about lines, I want you to think first and foremost, when we get around to it, 1, tackle slope, 2, y-intercept, 3, x-intercept, roughly in that order, okay? So first thing we're gonna do is we're gonna write a line. Let's say you have the points 2, 3, and I don't know, -4, 11. And we need to define the slope of that line. The first thing we're going to do is find slope. Okay? Slope, again, is the rise over the run, the change in x, change in y, some use delta y, over delta x, or y2 minus y1, x2 minus over x1. So we'll do this. So we'll do y2, 11, minus 3. So again, x point, y point, x point, y point, y minus 3 over minus 4, minus 2. So be careful you go the same direction. Make sure you don't go from here to here and then there to there. 11 minus 3, and then 2 minus minus 4 will change the slope. So 11 minus 3, 8 minus 4 minus 2 minus 6. So my slope is therefore 8 over minus 6. Simplify that, 4 over minus 3. And then sometimes out of convention, we put the negative on top. So we have this line, y equals negative 4 over 3, negative 4/3 x plus b. We're almost there, guys. We need to find what the y-intercept is. How do we do that? We can take any point. We'll take an x point generally and plug that in. So if at x is 2, I'd say y equals negative 4/3 of 2 plus b. A little bit unhappy number. Oh, I got to put the 3 in there, don't I? We'll get some more space. So I would say when we have 2, 3, y equals negative 4/3 x plus b. When y is 3, x is 2. And then I solve for b. So 3, negative 8/3 plus b. Add 8/3, 3 plus 8/3 plus b. So that would be 3 plus 2 2/3. So 5 2/3, or rationalize that, make it 17/3. Either of those would be fine. So my full equation, rushed ahead, my full equation would be y equals negative 4/3 x plus 17/3. Okay, so a couple of things. One with a line. Parallel lines have the same slope. This is really important. And perpendicular lines, their slopes are negative reciprocals. So if I had another line that was parallel to this, I'd have negative 4/3 x. I could say negative 4/3 x, I don't know, plus 2. It has a different y-intercept. Still has a negative slope, but it has a different y-intercept. If the lines were perpendicular, I've got a couple more things to get through here. If the lines were perpendicular, the slopes are negative reciprocals. Meaning I take whatever this is, I flip it, and then I make it the negative of whatever it was. So if I had negative 4/3, it'll become 3 over 4, but in this case, positive. If I had a slope of 7 over 8, the line that's perpendicular, I'll flip those and make it negative. Okay? Now, I want to talk really quickly and just find a problem or two here for what's called math modeling. Let me get my piece of paper here. So math modeling, again, is basically, you got an equation, you got something a little bit funky, and you're trying to say which of these things, how do I write an equation that models this? Or if I have an equation, which of the things best represents it? So, I don't know. Let's take number 6, just for example. This is one the SAT loves because they love to combine math and science. So the formula to convert temperatures from the Celsius scale to the Fahrenheit scale is C times 9/5, or 9/5 of C plus 32 equals F. What is the meaning of the 9/5 in this equation? Well, there are 3 ways to go about this. One, you may just figure this out on your own. That means, well, I'm not even going to tell you. I'll let you think about that. Or you can look through the answer choice and say, is that true? Or, and here's my favorite way to go about this. So you can read this through and think, is this right? Is this right? Is this right? Is this right? My favorite method for any problem like this, you're going to be surprised, I know, is to plug in a number. And so what we're going to do is use C equals 1 and then C equals 2. So we're changing C from 1 to 2 and say, how does F change? So if C is 1, then we're going to say that F is 32 degrees plus 9/5 times 1 is just 9/5. Or when C goes to 2, we now have the degrees in Fahrenheit is 32 plus 9 times 2, 18/5. So we went from, and I can make this easier too, 9/5, 18/5 is 9/5 plus 9/5. So each change in Fahrenheit is equivalent to 9/5 in Celsius. When we went up by, do we go up by 1 degree in Fahrenheit, we went up by 9/5 in Celsius? No, we went up by 1 degree in Celsius and went up 9/5 in Fahrenheit. So for some people, these problems are really easy, super transparent. For other people, it's like, oh my gosh, wait, what? And I love, love, love thinking these through, but more often, plug in a number to make it really concrete. So I can literally just model myself. If I change this from 1 to 2 or 0 to 1, what changes, okay? I'll make a note, we have a number of these things. These math modeling things are a really big deal. I'll put these online for you guys as well. They really like these problems, particularly on the SAT. Not such a big deal. On the ECT, you'd more likely have to just solve this. Plug in this number, plug in that number, see what pops up. SAT tends to be, for these kind of things, for the linear problems, a lot more conceptual and asking you to think about what's going on here. So a little bit more abstract, maybe a little bit more difficult. If you can plug in numbers, you keep it concrete. But these are all problems from my SAT workbook, and I'll send those guys around as well. Okay, where's my list? Where's my list? We're getting through there. All right, so we talked about slope, finding the equation. Oh, I should say a problem that pops up a ton for both SAT and ACT with lines is finding the point of intersection. So let's go back here for 1 second. Ugly problem. If I wanted to find the point of intersection for that, what I would do is say that, note that it's going to be an XY pair that's true in both equations. So I could arguably use the answer choices and plug them back in. Or if it needs to be the same X and same Y, so that when I plug in this value for X, it equals this. When I plug the same value for X, it equals that. The easiest thing to do, because I need to have the same Y values, is to set this equal to this. What gets the number here, what gets the same number there, and say -4/3 X plus 17/3 equals 2X plus 5. In the interest of time, I'm not going to go through that whole thing, because with 17/3, frankly, it's a little bit of an irritating number. There's a couple other things that I want to talk about. We did a kind of an abstract problem talking about quadratics having 1 real root, 2 real roots, no real roots, or 2 imaginary roots. And I want to point this out. This is, again, this is a pretty sophisticated thing, but worth doing. With 2 lines, we can have 2 possible outcomes. We can have the lines intersect. We can have the lines be parallel, so no points of intersection, or we can have 2 different lines and they'll literally be the same line, which means an infinite number of solutions. So again, to intersect, all that we need is just different lines, right? Different slopes. To be parallel, we need the same slope, but different y-intercepts. And so those things will be parallel and have no points of intersection. To have infinite ones, we need the same line twice. And I'll show you what they do on both the SAT and the ACT. They'll write something like, for what value of k does 2x minus 3y equals 4 and 6x plus ky equal 12 have multiple answers or multiple solutions? Well, again, with a line, we can have 1 point of intersection, no points of intersection, or all of them. So multiple just means infinite. So that means, like here, I need to have the same equation twice. All we did here is multiply times 2 times 2 times 2. So here we multiply, or they multiply, is times 3 times 3. So in order for this second equation to be the same thing as the first, I need everything to be tripled. So if this was minus 3x, I now need minus kx, excuse me, minus 9x. So that means that k times y, not kx, 9y, excuse me, I need to triple this. So I need to go from minus 3y to minus 9y. So ky has to equal minus 9y, so k has to equal minus 9. Again, actually pretty simple math, a funky concept if you've never seen that. You're like, what are they asking me to do? So again, some easy stuff with lines, some hard stuff with lines. And last 2 tricks I want to do really quickly are what are called systems of equations or linear combinations, and this kind of funky thing I call them factorials. In real mathematics are called Eigennumbers. It's a German mathematical term. You don't care, but I'm going to show you this kind of neat trick. Okay, so here's a typical system of equations, right? You make this equation based on, we're not going to go through, you make this equation and then you're trying to solve it. And in school, you've been taught a couple different ways. You could put one thing in terms of another, right? And then substitute it in. You could also have multiplied everything by the same amount of terms and get them down. But oftentimes, there's a really clever, elegant way to go about this. And so let me show you what this might look like. I only have 3 of these. These are kind of fun to do. Okay, so here's an example. So you might easily want to do x equals 2y plus 4 and plug that in. And that'll work, and it's perfectly fine, right? Or you might multiply the top times 3, but I'm not going to do that. What I'm going to suggest here is that for a lot of these, we can use linear combinations, meaning we either add them or subtract them. I'm going to start with an easy one, I'm going to get harder ones. If I add these, you see that there's minus 2y and plus 2y, so that's going to cancel out. X plus 3x is 4x. This will cancel out, and I'll get 10, and then x is therefore 10 over 4, or 5.2, or 5 over 5 halves. Super easy, right? 10x plus y equals 8. 7x minus y equals 9. How do I get 3x is the question I want you to ask yourself. How do I get 2y? Well, again, I could multiply this times 7 and that times 10, but let's not do that because that's a whole bunch of algebra that I don't want to do. So adding them obviously wouldn't get me 3x, so I'm not going to, so I'll think that first thought, well, that's 17x, that's the wrong direction. So let's now try minusing, subtracting. 10x minus 7x, 3x, plus y, minus minus, so it becomes plus, 2y, 8 minus 9, negative 1, and there's your answer, okay? A harder one, 4x plus 5y equals 11, 7x minus 6y equals 4, find 15x plus 4y, okay? Now, like I said before, we can first add those. That gets us 11, so that's not right. I subtract them, gets me minus 3. Shoot, that's not right. So I got to be a little bit more creative. So what could I do here? So the question I'm asking myself is, how do I get to 15 if I got 4 and 7? 4 and 7, how do I get to 15? And some of you have already figured out that what I could do, I'm going to multiply the whole thing times 2. So that'll become 8x, because 8 and 7 is 15. That'll become 10, that'll become 22. So 8 plus 7, 15, 10y minus 6y becomes plus 4y, and then 22 minus 4 becomes 18. Now you might be asking yourself, well, that's great, that's really clever, but how do you know it's going to work that way? Because they design it this way. They love having problems where they get you and me and everyone else taking the test to jump through the hoop and do all this work like I had on that first page, and suffer and suffer and suffer, and then they put in some little trick and they pat themselves on the back for being clever, and you're like, you've got to be kidding. So I'm going to do one more like this, and then I'm going to share this factor FOIL thing I talked about. Okay, this one is also curveball, but we get some of these ideas from what we know about how the test makers like to throw us curveballs, so we try to anticipate, we try to predict, try to help you guys out. What I'm going to suggest is we're going to add these. Does anyone see how to get to 7a plus 3b? Yep. We divide everything by 3. 21 divided by 3, 7. 9 divided by 3, 3. 30 divided by 3, 10. And there's our answer. Okay. So we've gone from some really easy stuff to some really hard stuff. I want to throw one more wackadoodle thing at you. And here we go. Okay. If x plus 3 times x plus 5 equals, ooh, I'm going to make this weirder. X plus 3 times x plus b equals x squared plus 7x plus q for equated. I don't know. What does q equal? So Q for quirky. Okay, so we're going to take this. I started to say Q for crazy, but that's not how you spell that word. All right, so Q for quirky. I'm going to FOIL this out. So what we talk about here is what I call factor FOIL, where we're either going to factor both sides or FOIL both sides, so we can compare them. So I'm going to multiply this right side out. First, outer, inner, last. Q for Quirky. So I'm trying to find that. Here's the trick. Eigennumbers, again, really nerdy. I had a friend who told this to me, is a German word for each. And the idea is this. The x squared terms equal each other. And I could probably talk you into that. The non-x terms equal each other. This, of course, is the y-intercept. When x is 0, x is 0. X is 0, 0, 0. So those guys would equal each other too. But it also means that the x to the power 1 terms equal each other. So I can set them equal individually. It's a really funky thing. I have never seen anyone who learned this in school. I don't know why it's on the test, but it seems to be. So check this out. Bx plus 3x equals 7x. Bx equals 4x, which means, of course, that b equals 4, which I then can take up there and say 3 times 4 equals q. Like, really? Pretty fun, huh? Let's do another one. X squared minus y squared equals 12. X plus y equals 5. What is x minus y? Remember, we did this before, the difference of two squares. X plus y, x minus y equals 12. I can put that in over there and say 5 times x minus y equals 12. So x minus y equals 12 over 5. So again, I call these eigennumbers, or a factor FOIL really is the way I think about them. So if we have something where I can't factor that very well, so I'll FOIL this out and set them equal. This, I'm going to factor both sides and then put one in terms of the other. So these show up a lot at kind of the very end of a math section, considered pretty hard problems. 6 plus 2i times 4 plus bi. This is the last one I'll leave them. This is really terrible. Equals 12 plus 2i. What are we going to do with that? Let's find out. 24. I have to change that. Let's find out. We can do that. 24 plus 6bi plus 8i plus 2bi squared equals a plus 2i. Okay, I squared is -1, so 24 plus 6bi plus 8i minus 2b equals a plus 2i. It might have made this too hard by half, guys. We'll find out. So here's the fun part. These are real numbers, and these are imaginary numbers. Okay? This is a real number, and this is an imaginary number. So this means that 6bi plus 8i must equal 2i. So 6bi minus 8i, this might just work out. Never know when you make these things up on the fly. So that means that b has to equal -1. Remarkable. And then over here, 24 minus 2b equals a. If b is -1, a equals 26. That's a really hard problem. I feel a little bit bad leaving you guys with that. But again, the basic idea, the most typical thing for these, I'll do this one more time, is that we multiply these guys out. Whatever. We multiply these guys out, and then we put the like terms together. Okay? Whatever I did. xk plus 2k equals x squared minus 3x. That's the part I'm looking for, that the 2x plus kx equals the minus 3x. This tends to be like the very last problem oftentimes in the non-calc section of the SAT. Pretty funky stuff. Hopefully that didn't completely blow your head clear off your shoulder. Like I said, I wanted to throw at you kind of all the really funky tricks. If you're a little bit blown away by the end ones, don't worry about them. These are problems like we talked about at the very beginning of this, that we want to be strategic about what questions we do, what questions we don't do. Fundamentally, always focusing on getting correct the questions that we know how to do well, not rushing, not making some mistakes, not worrying about the hardest problems, but really taking care of business. So we want to make our free throws, we want to make our layups. Nobody has to do heroics, make a three-point shot at the very end of things. Next week on to a little bit more math, but again, I'll put an SAT and an ACT online for folks. And again, if you're looking to go through any of the past things about trigonometry or last week's stuff about test anxiety, on our email, if you go to Prep Matters TV, you go to the link, find the class page for SAT, ACT, and scroll down and you'll find those recordings there. Have a great week, folks. Be well, stay well, and I'll see you next week. Bye-bye.